Hello, my name is Brian Bogue, and on behalf of my team, I would like to show appreciation for your interest in our work, titled Selection of Non-Invasive Features in Wrist-Based Wearable Sensors to Predict Blood Glucose Concentrations using Machine Learning Algorithms. As you may have suspected, the principal motivation for this investigation into continuous and non-invasive glucose monitors is for the regulation of blood sugar in diabetics. Diabetes is a condition which is estimated to affect 450 million people worldwide, and individuals with diabetes are prone to swing from low to high levels of blood sugar, known as hypo and hyperglycemia respectively. In order to manage this condition, individuals must be able to track their glycemia, which means raising or lowering their blood sugar accordingly. The most popular method by which to track blood sugar is through the use of traditional glucometers. These family of devices utilize enzymatic reactions to produce electrical signals readable using the meter, and are prized as the market gold standard for their high specificity. However, they require invasive sampling methods in which the user pricks one's finger to draw blood. This practice results in few measurements per day, and the single-use disposable sensors produce recurring costs and waste. Therefore, there is a need for non-invasive continuous glucose monitoring methods, as current methods are inconvenient due to their invasive sampling procedure, which is painful, costly, and practically leads to few discrete measurements per day. Over the last decade, there's been a great deal of progress in an alternative methodology called the glucose oxidase needle, which is a continuous glucose monitor. This principle is based on taking an enzyme-doped platinum electrode needle that is inserted into the body and reads the glucose levels at the interstitial fluid. Several devices have become commercially available which implement this approach. And this approach is considered minimally invasive since all you need to do is insert the small needle once every 2 weeks, after which the sensor needs to be disposed of and replaced. The natural development is then to take the success of the continuous glucose monitors and attempt to find a non-invasive solution. In our study, we aim to explore multiple off-the-shelf wearable sensors that could be implemented in the form factor of smartwatch-like devices to create a feature set sufficient for blood glucose levels predictions utilizing machine learning algorithms. Our hypothesis was that the sensors chosen would provide a sufficient feature set to accurately predict blood glucose levels in healthy individuals. The benefit of such a device would be that it is compact, non-invasive, and does not produce recurring costs or e-waste. Here we can see a flowchart of the proposed sensors. For example, the Delphin, which provides a skin moisture, and the G-Skin, which gives a heat flux. Some of these sensors already have a form factor that is compatible with a wristwatch-like device, like the Empatica and SpO2 monitor, which gives heart rate, EDA, skin temperature, and SpO2 respectively. The only exception being the blood pressure cuff. Only one not shown on here is the DHT11, the ambient and humidity temperature sensors. These 6 sensors provide 10 unique features with some redundancy, which ensures accuracy, and these features are then used with the Freestyle Libre 2 to train a regression model, which is able to predict blood sugar. This pilot study aimed to validate our hypothesis of using a multi-sensor array to predict blood glucose using several regression-based models and a combination of 10 unique features. After training and validation of the best performing models, all our predictions fell within the clinical range. Future work will focus on collecting a larger dataset in order to make further conclusions about this approach.